Hello and welcome. We're going to look at chapter 28, Electromagnetic Induction. So, just after the discovery that an electric current has a magnetic field, scientists try to reverse this process. The problem was a current produces a permanent magnetic field as the current flows, but scientists really struggled to get the reverse possible. And then Michael Faraday and a few other scientists simultaneously got to this, where they realized the following observations. If they had a wire connected to either a lamp or a voltmeter or something like that, they realized that there is a point where a electric field can be current can be generated. Okay, but there were certain conditions that they saw. So they saw that if we bring a magnet close to a coil, okay, that there is a current. When we do it slowly, that current is small. When we do it fast, that current is big. Also, if we increase the number of loops of the coil, that has a big effect. And also, if we increase the area of that coil, that also has a big effect. If we make the area smaller, okay. So these were some of the observations. Another way that we can observe this is to take an electric motor and to manually turn it with our hands once it's connected to a voltmeter. We will see that while we are turning, there is a voltage being generated, but the moment we stop turning, the voltage would stop. Another alternative way of doing this is when we connect a wire to a ammeter or a galvanometer, and we put that ammeter or that wire through and move it up and down through a magnetic field. We also see the moment we move the wire that there is a current. Now, the faster we move the wire and the more of the wire that's inside the magnetic field, the bigger the current will be. So now we're going to try and look and explain why these observations happen. If we look at our coil, so we've got a magnet and we bring the coil closer. Here we've got a lamp that shows that there's a current flowing. And remember, when there's a current, there's also a voltage. Now, what is important to know is that there is a magnetic field, also called a magnetic flux. Now, the word flux means flow, so there must be, the magnetic flux refers to the field lines. Okay, so there must be a change. And do you see how the field lines cut through the coil? Okay, so it's only when the magnetic field lines cut through the coil and while it's busy moving that there is an EMF and a voltage or a current produced. So it's either when it's moving in and it's cutting more of it, or when it's moving out and it's cutting it backwards. But there has to be an interaction between the field lines and the coil. Now, the direction of this current can be used by using the right-hand generator rule, where we use F for the force that I'm applying, B for the direction of the magnetic field towards south, and I for the direction of the induced current. So now we'll be looking at magnetic flux and magnetic flux linkage. In our previous chapter, we spoke about the magnetic flux density, which is basically the amount of magnetic field lines that is flowing, okay, or the magnetic field lines. So now we're going to look at, that's the magnetic flux density. So if we want to think what is the magnetic flux, flux has this symbol, and it's basically if we have a certain magnetic field going through an area, okay, the amount of field lines going through the area. So the magnetic flux is the magnetic flux density going through a specific area. Now once again, since we have our forces at right angles, our magnetic flux needs to be 90 degrees to it. So we can actually say that our magnetic flux can be BA and then cos theta. So what happens is, if it is at 90 degrees, cos 90 is 0. But if it's cos 90 is maximum. But if it's parallel to, if they're going this way, then there's going to be 0 flux. So maximum flux is when the magnetic field goes through the area of the coil. Okay, and then we get the magnetic flux linkage. Now the magnetic flux linkage, this is now, magnetic flux is through one coil, but one loop. But the moment we have multiple loops, okay, we times the number of loops with the magnetic flux, and the magnetic flux, we call that the magnetic flux linkage. So to calculate the magnetic flux linkage, we take the same formula, BA cos theta, and we times it with the number of coils. Now let's just quickly look at units. We know that magnetic flux density is measured in Tesla. Okay, so it's going to be Tesla per square meter, Tm squared, and we define that as a Weber, WB. So we spell Weber, W-E-B-E-R. Okay, so when we take the Tesla times the area, we get Weber. Okay, and the magnetic flux density is just the amount of multiples of Weber that we have. So whenever we change anything in the magnetic flux, remember there has to be a change. So when we have a changing magnetic flux linkage, okay, by either changing the area or the strength of that magnetic field, or the angle at which the magnetic field and the area interacts, we are changing our magnetic flux density. You can technically change the amount of coils, but that hardly happens. So it's either the strength of the field or the orientation of the field. The area of the field also rarely happens, but any of those changes causes a change in the magnetic flux linkage, which causes a EMF and a current. So most of the time they either vary the magnetic field by taking it in and out. As we take it in, we have an increasing magnetic flux density, and when we take it out, we have a decreasing magnetic flux density. Or they rotate your coil inside your magnetic field, changing the area, and that's exactly what they do in a generator. Not the area, the angle between the magnetic flux and the area, the surface area of the coil. Next, we will be looking at Faraday's law of electromagnetic induction. Now, Faraday's law simply says that the EMF that is induced is directly proportional to the change in magnetic flux linkage over time, okay, or the rate of change of the magnetic flux linkage. Now the proportionality constant here is 1, so we can actually make this our formula. And by substituting what we had earlier, we know that the change in BA cos theta. So any change in that over time is going to cause a EMF. Lenz's law. One of the interesting observations is when we look at the polarity, when I put a south in, okay, I get a positive voltage. When I take the south out, I get a negative voltage. If I flip my magnet, when I put this north in, I get a negative, and when I pull the north out, I get a positive. Now remember, Lenz's law says that the current that is induced is going to oppose the change that of the magnet. So inside this coil there is a current either flowing up or flowing down. Now using the right hand rule for a solenoid, where my thumb points the direction of the magnetic field in north and my fingertips point the direction of the current flowing through the solenoid, we can determine this magnetic field produced in the solenoid. So inside this solenoid, this coil, a magnetic field is produced, and that field will always oppose what I'm doing. So if I want to bring a north in, the field wants to produce a north. So it will spin the current in the direction to oppose me entering the north. Now using our right hand rule, okay, the north points towards, so we turn our hand, so our right hand, so that our thumb points towards the north of the magnet, and we see that it would flow downwards through the coil. Okay, and if it flows downwards through the coil, we see that that's a negative reading. Now if I pull it away, I get the opposite. If I take my north and I pull my north out, I get a positive reading. Okay, so a positive reading, it wants to prevent me from pulling out my magnet, so it attracts it. Now when I have a south, it means the north is on this side. So placing my thumb, my right hand, so that my thumb points to the right, we can see from my knuckles to my fingertips that the current flows up here, creating a positive flow of current. So Lenz's law is simply that the system, the current that is induced, will always oppose the change creating it. And even likewise, if I go turn the south side, we see the same thing happening. So one of the applications where we use electromagnetic induction is in what we call eddy currents. So if you haven't heard of an eddy current, the eddy current is whenever I have a piece of metal inside a magnetic field. Okay, so that metal is like a disc, and let's say we spin that disc. Normally the disc would just continue to spin until friction stops it, but the moment I bring that disc into my magnetic field, it stops automatically. Now what happens is we have the magnetic field creating a current, and that current creates a secondary magnetic field that opposes that one. So what happens is we actually produce a current. Now that current also has a heating effect, and that is how induction heating works, where we have a plate on the stove that doesn't heat up, it just has a current, and in your induction pot it creates a current inside the base of the pot, which in turn creates a heating effect. So eddy currents, we use it for any electromagnetic braking on trains, we use it for induction stoves, and there's a lot of other applications where we use this eddy currents specifically. Last but not least, we also obviously use this to generate electricity. So as part of the presentation, I'm going to send you two video clips, one that describes how a electric generator works, and secondly one that describes how does the um, the graphs of it work, how we draw the graphs, and that would bring more clarity to that. It's better if I send you a demonstration where they visualize it better than what I can visualize it on the board. Okay, so that would be chapter 28, and if you've got any questions, please let me know.